You have vectors, but how do you turn them into show me similar items? We'll build a tiny working version of that idea. You know the pain. You have a bunch of sentence or image embeddings, and you want the closest matches fast. By the end, you will understand the simple math behind cosine similarity and how to turn that into a ranked search in Python using progressively better tricks. I'm Professor Pi, teaching AI foundations with simple Python. Nearest neighbors for embeddings solves the common task of similarity search. People use it for search, recommendations, clustering, and deduplication. The idea is to treat each item as a point in space and ask which points sit close to a query. Success looks like retrieving a small list of genuinely relevant items in a fraction of a second for a single query. At its core, cosine similarity measures angle, not length. Two vectors pointing the same way are similar even if one is larger. A tiny example is two toy embeddings for two short sentences. Cosine handles the fact that embeddings vary in scale better than raw distance in many NLP use cases. We will build this in 5 steps. First, I show a single cosine calculation. Then we rank many items. Then we select the top k efficiently. Next, we normalize vectors, so cosine becomes a fast dot product. Finally, we plug into scikit-learn nearest neighbors for a more practical retrieval. Keep your Python familiarity handy. The code stays simple. This snippet computes a single cosine similarity between two toy embeddings. It defines two short vectors, then computes the dot product and the two vector norms, and divides the dot by the product of norms. The important idea is that the dot product measures alignment while each norm measures length, and dividing produces the cosine of the angle between them. In spoken form, the code calls NumPy dot, which computes the dot product between the two vectors, and NumPy lineout norm, which gives vector length. If either norm were 0, the code would guard against division by 0. This example is the smallest building block. One query, one candidate, one cosine score. Now we expand to many candidates and produce a ranking. This example ranks all items by cosine similarity to a query vector. It arranges the candidate embeddings as rows in a matrix and computes similarities against the query in a single pass. Conceptually, it computes a dot between the matrix and the query and divides each result by the candidate norms times the query norm. Practically, the code shows how computing all scores at once is far faster than looping, because vectorized NumPy operations exploit optimized C code. After computing the similarity vector, it uses sorting to produce indices in descending order, so the most similar items come first. If you change batching or the candidate count, the memory and compute pattern changes, but the ranking logic stays the same. Next, we pick only the top results efficiently without sorting the whole list. This code selects the top k nearest neighbors using heapq and largest. It computes per item cosine scores and then uses heapq and largest to return the highest scoring items and their indices without fully sorting everything. The key idea is that when k is much smaller than the number of candidates, you save work by only maintaining a small heap. The snippet shows how to call heapq and largest with a key function that reads the pre-computed similarity list, and how to unpack the returned pairs into indices and scores. If you increase k, the heap grows, and the operation behaves more like full sort. If k is small, like 1 or 5, this is a simple and practical speed win. Now we make cosine search faster by reducing it to a dot product. This snippet normalizes vectors, so cosine reduces to a fast dot product. It transforms each candidate and the query to unit length by dividing by their norms so that cosine similarity equals the plain dot product of normalized vectors. The code shows normalizing the matrix by row and the query by its norm, then computing a single matrix dot vector product to get all cosine scores directly. This normalization lets you pre-compute normalized candidates once and then answer many queries with a single dot each. The practical payoff is lower per query latency and easier use of fast linear algebra libraries. If you skip normalization, each query must divide again, and numerical behavior can drift. Finally, we look at a standard library implementation. This snippet uses scikit-learn nearest neighbors with cosine distance to retrieve neighbors. It fits the nearest neighbors index on the candidate embeddings, and then calls the neighbors method to retrieve nearest items for a query. The important detail is that scikit-learn expresses the measure as cosine distance, which is 1 minus cosine similarity. So the code handles the transformation internally and returns nearest indices and distances. The snippet also shows the parameter n neighbors, which controls how many neighbors are returned, and that increasing n neighbors returns a longer list and slightly more work. Using this library gives a convenient, well-tested implementation and an easy path to benchmarking. Mapping this toy pipeline to a real system is straightforward. Pre-compute normalized embeddings for your corpus, serve them from memory or a vector store, and run queries through either a fast dot product or an ANN index for scale. The same ideas apply whether you have a few hundred items or a few 100,000. Recap. Nearest neighbors with cosine finds items whose embeddings point the same way. Use it when similarity matters more than raw magnitude, like semantic search or recommendations. One caveat: cosine handles direction, but not all notions of relevance. So inspect your results and embedding quality. Next step, scale this exact approach by moving to an approximate nearest neighbor index and tune its parameters. For example, using FAISS and experimenting with nlist and nprobe to trade speed for accuracy. If AI foundations in Python help, subscribe and watch the AI Foundations videos.